So in today's video we're going to look at the difference between the generation 1 DB04r and the third generation module. So we have the first generation here, and interestingly, looking at the website, although on this module you have the rocker switch at the side, the website actually says it should be on the top for generation 1. So maybe this is actually a aftermarket version, a copy of the version 1, I don't know. But anyway, the major differences for the power is you've got obviously a rocker switch on the side on the first generation, and on the third generation we have a slide switch which you can't really see on the top. So we can move the slide switch there to give us a power light there, and if you look, none of the Qs are lit up. If we turn the power on for the generation 1, we have a yellow power light and then four red LEDs showing you the Qs. So let's just quickly go through the features of the two and the differences. So on this one you have a hidden button on the front that allows you to sequentially program the 4 Qs. So in other words, you press the button and you hold the program button in, and then on the remote you select which button you want it to start from, and then the controller will actually then program the other Qs sequentially. So if you pressed obviously the program button in and you pressed 4, it would go 4, 5, 6, 7. So 4 becomes the first Q, and then it sequentially writes. You can do exactly the same on this module. There's a little hidden switch, sequential program switch up there, and again you can do the same thing. So you can start with 4 and it will carry on and write these sequential numbers in for you. On this one obviously we have a yellow power light rather than a red power light at the top. Now if you look at if we fire the modules, you'll notice that in the first generation the light goes off, and in the third generation a red light comes on. If we now put an igniter in to the first module, you will see that the red LED gets brighter, substantially brighter, and again if we fire it will go out. If we now, sorry, that don't mind me destroying the tripod stand. If we now move that into the third generation unit, you'll see we get a green light come on, and then if we fire it goes red. So slightly different there. We have a green light for continuity and a red light for fire, whereas this one is a dull red LED for always on, and then a bright red LED for when you've got continuity. Other things that are interesting to note is there's more features on the third generation. On the third generation, if you turn over, you have a series of buttons per Q that allows you to actually tell each Q what number you want them to be. So for example, rather than do whole sequentially, at the moment, for example, there should be 1, 2, 3, 4, but say we want to make Q2 actually Q4 as well. So we hold the button in for Q2, which would be there. Sorry, I'm not in focus. So if we hold the button in for Q2, you'll notice we get a flashing light. We can now hold button 4 and then release the controller, and you see that on FB4. So now we can go 1, 2 is nothing, 3 is that, and then 4 is those two at the sides. So that allows us to program individual Qs, which could be quite useful if you're doing set pieces and you've got left and right, and you don't want the Qs to run sequentially because you want to go left and then right and then left and then right. So you could actually effectively program this 1, 3, 5, etc., and not waste the middle Q, because if you've paired the two modules up. Other things to note is that this has a low battery warning. The red LED at the top starts to flash quickly if you end up in low battery. This one does not have that. You can also, on this one, although I'll discuss this later in the video, the programming of the individual Qs does not have to be on the same remote. You can actually program different Qs to different remotes if you so wish, which again is another feature you can't do on this one. On this one, whatever the remote is that sets the first Q, all of them will be the same remote. So that pretty much sums up the difference in features. That it's in terms of the look, they are pretty much the same. There's a slightly longer aerial for the third generation, and I have to confess the way the third generation handles the aerial is just far better. The third generation, sorry, than the first generation, which has it sort of randomly screwed on with a wire leading to the circuit board. At least this one, the antenna actually goes onto the circuit board, which is quite a nice additional feature. And the switch is actually properly soldered, whereas on the first gen unit you can see they've actually snapped some of the board off to get the switch in and then just soldered it on, which seems a bit of a rough way of attaching the switch. So in theory, looking at this, you would think that in terms of power consumption, the third generation would be better because it's not running all the LEDs constantly if you haven't got a queue in. But we'll look at that later in the video. Something else the module also claims to have is a reverse battery protection. I can't see it in the circuitry. I think what they're relying on is if you've put one battery in backwards, you'll get a low voltage because the low voltage alarm will go off, the little LED will go off. But there is nothing in the circuit that protects reverse protection. So if you've got all the batteries in wrong way around, I think you would damage the unit. So I thought we'd start our analysis just by looking at the photograph of the PCB, and then we'll look at the schematic in a minute and actually look how it works. So first of all, let's quickly label the components. So at the top here, we have the power switch, and next to that, the two terminals is the LED, the red LED for the power. Now this is a soft power LED, which means, as we'll look in the schematic in a second, this is not connected directly to the power rails as such. This is connected through the microcontroller, so we can actually make this intelligent if we wish. The two terminals next to that, they are the switch terminals for the sequential program mode button, which is at the front of the device again, and we'll look at that function in a bit later. Moving down here, we have our regulator section. So this is providing the 5-volt rail for our microprocessor, our EEPROM, and our radio module. So this was not the same as first generation. The first generation used everything at 6 volts. This one has a 5-volt regulator, so we've got a separate power line for the logic circuitry. And just looking at that quickly, we have a large decoupling capacitor, which is about 100 microfarads. That's really quite large. Then we have a smaller one here, which is on the 6-volt line coming in. Next to that, we have the 75501 5-volt regulator. Let's have a quick look at the datasheet for that. So it's a low dropout regulator. That's important because usually with linear regulators, you have to have a couple of volts clearance for the regulation. So you might find that if you've got a 5-volt regulator, you might need 7-volt input or 8-volt input. With this, we've only got 6 volts in because that's what our batteries are supplying. So we have very minimal headroom between the 5-volt rail and the 6-volt input. So we have to have a low dropout regulator to try and make that as small as possible, that difference. And when we look at the low power mode that it enters, it can actually decipher when you have low batteries, and we'll see how they're doing that and what that's set at later on in the video, and that will tell us whether or not the regulator actually manages to withstand the lower voltages as the batteries decline or not. What I wanted to show you though is the packages, because we have a SOT89 package, which is what's on the board, but we also have a TO92 package, and that, if we look at the board, is not actually populated. That's empty. That's that package there. So they've actually designed this for whether the TO92 is in production or whether the SOT89 is in production. So if they have any problems, with either one of those in production, they can just change them on the board without having to respin the board, which is quite clever. Let's just remove some of this so we can see what we're doing. So next to that, this row of 2 resistors and a capacitor, this is our low battery sense circuit, and then we'll look at that in a second. Over here we have our RF receive circuit, and you'll see this version now they've actually made a nice pad there which they screw the aerial onto rather than a rubbish solder link, which was the previous version. These 2 terminals here are the crystal oscillator underneath. Sorry, I forgot what it's called then. Crystal oscillator. Then we have is it Synoxo, I think they call it. We had the version 4 series on the first gen. We now have the version 5 series. I haven't got the actual datasheet for this because the actual chipset is the SIN 590R, not the 531R. But the 590R I could only find in Chinese, so I couldn't actually find the exact datasheet, but it's very similar. And I'm not too sure what the difference are in terms of features. It looks to me like it uses a lot less external components to the previous chipset, and it has better noise reduction, etc. So maybe that's why they've chosen it, or maybe the other ones are now gone legacy, so they can't use them. So that's very similar to our previous module. We then have these 4 big white blocks in the middle. These are just switches for the Q programming, so we won't worry too much about those. Right, now we have underneath that, we have these other 8-pin chipsets. These are the MOSFET chipsets, so these are actually what's creating our firepower. They are the 9926, I believe. Yeah, I couldn't actually find which manufacturer they are on the chip, but I think they are the cheaper Chinese versions rather than the Fairchild versions, which are the dearer versions, and they're slightly different specification as well. But they're N-channel MOSFETs basically, and you can see that we have 2 per package. So if you look over here, we have 2 drains, drain 1 and drain 2, and then gate 1, gate 2, and source 1 and source 2. And we have effectively, well, they say continuous drain count up to 6 amps, but you've got to be careful with that because you can't just draw 6 amps out of it. You have to obviously be careful of what the temperature is in terms of the junction temperature of the chipset, of the die of the chipset, and of course the package of the chipset. So you need to work out using your temperature calculations whether or not you can draw 6 amps. They've obviously worked out how they can draw 2 amps for a short pulse. And if you look at the board, I didn't show you the vias. That's a bit of a shame because usually it gives you a layout on the board. If on the actual board they've got, you can just about see, I'll draw it on for you, that under these chipsets they have created a pad that then links with thermal vias underneath to the ground plane behind to try and vent as much heat out of that chipset as possible. But sadly you can't see it from the front of the board. So what gives this also away is we can see here is one of our terminals, our wire terminals, and then that's got a really thick trace that goes into the first 2 drains. And then the second channel there you can see has another very thick trace that goes into the speaker socket, because there's the speaker socket there technically. There's another one there, and there's another one there. It's between these 2 big solder joints is where the speaker terminal sits. Now this also changes from the previous version, because the previous version they actually paired up each MOSFET on the same channel. So they had 4 MOSFET chips rather than 2 MOSFET chips. There's no reason to do that really. You've got enough tolerance on these chipsets to use 1 MOSFET per firing channel. So I'm not quite sure why in the first time they decided to pair them up. Moving on, let's have a quick look at the circuitry down here, because obviously here we have our microcontroller, and I think this is going to be a Puduk, I think that's how you pronounce it, microcontroller. They're very cheap Chinese microcontrollers, but I should say low cost, sorry, rather than cheap, because actually they're not cheap and cheerful as such. They do have a very good system and resources on them if you can program them, that, etc. Most of the data sheets are in Chinese, unfortunately, which doesn't help. But I think it's the PMS 154B, but it's impossible to tell because they've removed the markings on the chipset, so I can't tell exactly. But the pinouts look very similar to me, almost suspiciously similar. And then down over here we have our EEPROM, and again this is going to be an Atmel chipset. I think the previous version was an Atmel chipset as well. Interestingly, this one has been listed as not for new design, so clearly this is one that's going to legacy shortly, but it's a very standard one. We've got the address pins, and then we've got the data pins, and etc. Write protect. It's not huge, because if you look at it later, when we look at the memory mapping, it's only 2K. When you look at the memory mapping, you'll see why they've only got 2Ks, because it actually doesn't actually store much data realistically. There's only a few columns of data in it. Moving on then, we now need to look, we've done the radio, we've done all the chipsets, that's everything done. So now let's look at the schematic, and what I've done, I've broken it down and labelled it so it looks a bit neater, so it's not wires running everywhere. Let's look first at the microcontroller, because that's the centre of everything we're doing. So we can see that the first 3 pins of the microcontroller look at the switches. So these are the back Q switches, which control the programming of the individual Qs, and the front sequence programmer. That's not the power switch, that's a separate switch. Then we have low power sense on pin 5, which we'll look at again in circuit. We have radio in on pin 7. Pin 6 is our red power LED. So again, as I said, that's a soft power LED because it's being controlled by the microcontroller, not by the 5-volt rail. And then pins 14, 13, 12 and 10 are our various gates for the firing of the MOSFETs. And the last thing, pin 9 and pin 8, go to our EEPROM, our external memory. So let's first of all have a look at the 5-volt regulator. It's not a particularly difficult circuit. We've got obviously our power switch coming in from our 6-volt supplier. Then we have our simple 10 nanofarad capacitor. I think it's 10 nanofarad, so I can't measure the capacitors easily in circuit. We have our 7550-1 regulator, and then we have a massive 100 microfarad, I think it is, on the output, which is very large. And you'll see later on in some of the traces when we look at the oscilloscope that I think that's deliberately done to help them out a bit later, and you'll see what I mean by that. And then we have our switch circuit on pins 1 to 3. Now this may look a little bit strange because pins 4, 2 and 1 all pull to ground, so that seems obvious, but yet our sequential program switch and our terminal 3 program switch actually are connected between pins 1 and 2 and 2 and 3, and that's not technically pulling anything down, because if these are all pulled high, for example, these all switch inputs on the microcontroller are all pulled high, then this is just connecting a high line to a high line. So how do you sense whether these switches are connected? And it's done very cleverly because they're changing the pull-ups and pull-downs and the setup of the individual legs of the microcontroller. And if you look at, this is a logic probe connected to those 3 pins, and we can see this is without pressing any switches. This is just what's happening on the microcontroller. So it's basically 3 stages that repeats very quickly. So the first stage is all 3 pins are pulled high. So that means they can detect whether switch 4, switch 2 or switch 1 gets pulled down, because obviously that will drop the voltage of that. Then stage 2 is pin 1 goes low, pin 2 and pin 3 stay high. And then the third stage is pin 1 goes back high, pin 2 goes low, pin 3 stays high. And then that repeats that pattern continuously. And by detecting which of these lines gets pulled high or pulled low, etc., within which stage the microcontroller is in that loop, they can detect which switch is being pushed. It's a very, very cheap, cheerful way of multiplexing switches. It's very low component count, that is. There is an easier way of doing it than you can do multiple switches onto one microcontroller point if you want, on one microcontroller pin. And I've given you an example of that up here. So what we've got a number of potential dividers. Effectively, we've got all our switches connected into one line, which is our microcontroller I2C line. But I've changed the weight of the resistor after them. And then this gets divided with a fixed resistor of 2K. And I've deliberately chosen multiples of 2 because then you can just put multiple resistors of 2Ks on there. So you don't have to add, you don't have to then buy 4K resistors and 6K resistors and 8K resistors. You can just effectively put more than one resistor in line to get those weightings. And you can see below I've written the voltage which this potential divider will have. So you know if you get 2.5 volts on that line, that will be the first terminal 1 switch. If it's 1.6 volts, that'll be terminal 2, terminal 3 if 1.2 volts, etc. That's another easy way. But of course the problem is you've got to have more components. It's slightly more accurate. You don't have to keep making the microcontroller go around in an endless loop to detect switches, because that's the problem. The downside of using this version of lack of hardware means the software has to do more work, and you've got to use more resources on the microcontroller, which is not always in the best interests of your circuit. But that's the way they've done for component count. Now our low power sense divider is very simple. So they've basically gone from the 6-volt rail, not the 5-volt rail, and they've put two high value resistors in a potential divider format, which means you have a very, very low current draw through this. This will be microamps probably. What's that? V over R. So you're looking at 30 odd microamps, tiny current draw, because you don't want obviously your low power detector to take loads of power, because that sort of defeats the point of it. But it also has a capacitor attached to it, and this is a very clever circuit because this is actually weighting the capacitance of here with the capacitance of the port of the ADC. And I'm not going to go into this, but if you Google this technique, you'll find this is used a lot when you're looking at low power sensing. So I'd highly recommend you look at that. I will maybe leave some links in the bottom so you can have a look to see how that works, because it works by moving the charge from one capacitor to another capacitor, etc. And now lastly, we have our firing circuit, which is very different from generation 1. So let me just quickly go through how this works. So we have our terminal queue up here, which we'll say is empty for now. So we have no igniter connected. The MOSFET here is not on, so there's no connection to ground here. So we've got no connection to ground, which means these LEDs, which is actually a bicolor LED, but they're backwards in the same package. So there's not two LEDs, there's actually just the one LED, but the two diodes are effectively against each other, but they're not in series, they're in parallel. So if we put a current across that way, we'll get the red LED. If we draw a current down that way, we'll get the green LED. So if we've got nothing connected, there's no potential difference here, so no current will go through the red LED, and equally no current will go through the green LED because there's no potential difference here. But there is a potential difference between the 5 volts here and the ground here through these two 2K resistors. So you've effectively got a potential divider which is burning about 1.2 milliamps constantly with nothing connected to the queue, and that seems a bit wasteful, if I'm honest. If we now add an igniter into this queue, we've then got 6 volts here, and that will then cause current to flow down through the green LED through the resistor into the ground. So that will then cause the green LED to light. If we now fire this, so we now pull this side down to ground, that will cause a current to flow from the 5 volt line up through the red LED and then down to ground through the MOSFET. And of course the green LED will go out because it's blocking current in that direction. If there's nothing in the Q terminal and this fires, we still have a ground connection being pulled here, so we'll still get a red LED because it will pull from the 5 volt line through the red LED and then down to ground. So that's what we've got. If you fire the channel blank without an igniter, you get a red LED to come on for the firing. If you put an igniter in the LED, it goes green. And if you fire with the igniter in, it goes red again. And that's the reason why, because of the way this circuit works here. Now, I thought it'd be interesting to look at the standby currents and the firing currents, because the problem you've got is in the field is if you leave this on, these LEDs are lit constantly. So you're constantly burning electricity, you're constantly using current to keep those LEDs lit in the field while you're waiting to fire the show. So I thought we'd do a comparison between the 3rd generation firing circuit and the 1st generation firing circuit. And you can see I've made a very crude model of both in this version of LT Spice, which is a circuit simulator. And at the bottom I have written out my findings in terms of the current flow, etc. So in the 3rd generation, all 4 queues without igniters is a 4.8 milliamp standby, and that's because of those two 2K resistors which I was showing you a second ago. So that's because current is flowing from this 5 volt line to 0 volts to ground, and there's nothing happening. That's all it's doing. It's just basically wasting electricity, wasting current. If we have all 4 queues with igniters in, we have 8.52 milliamp standby, because obviously we've now included an LED, the green LED, into that. And now if we look at the total unit with igniters in, so that's including the microcontroller and the EEPROM and the radio module and all the rest of it, which is drawing power, and I'll show you how I'll calculate that in a second because I've actually done some measurements from the unit, we have 17.22 milliamp draw. So that's quite a lot, but if we look at 1st generation, this is where it gets interesting. So the 1st generation firing circuit is actually more efficient when all the queues are empty. Even though there's a red LED on constantly, well, you haven't got no LEDs on over here, but you've got a constant red LED here, but it's a dim LED. you have a 0.8 milliamp standby compared to the 4.8 milliamp standby in the third generation. But this is where it gets more interesting. If we now put all 4 queues of igniters in, we get a total of 16.8 milliamp standby because you've got the bright red LEDs on all the queues, whereas our third generation has still got that dim green LED on all 4 queues. So you can see we've practically halved the current usage in the third generation. And if you look at the total unit with igniters in, we get a 31.5 milliamp standby. So again, if you look at the third generation, they're about halved the consumption than from the first generation. Even, and that's quite interesting in itself, the fact they've actually have improved the standby usage, current usage, even though annoyingly they've got those two 2K resistors which will constantly burn electricity without queues without any igniters in there, which is a bit of a shame. That seems a little bit of a drawback. However, in all fairness to them, to do it on the same component count, they've done the best they can. So hats off to them for doing that. So now let's quickly go through some traces from the module. What we have here is the power up of the module. So this is the 5-volt rail, and as you can see, this is the large capacitor very slowly charging, hence why you've got a very slow turn on. But other than that little spike down there, which is my bad probing techniques, that I've looked and I can't see any significant bounce from the switch affecting any other circuit part. So they have solved the bouncy switch, which is excellent because that makes things much more stable. So that's the turn on. This is a fire pulse, so now I'm looking at the 5-volt line. Sorry, I'm looking at past the regulator just to see if the regulator dips sufficiently when you draw a large current. So this is the firing pulse going through an igniter, and you can see you get a small drop of about half a volt on the 5-volt rail, the logic circuitry. But that's well within tolerance of the rest of the chipsets, so there's no reason to think that's poor design. That's just unfortunate. When you draw a large current from a battery or any power supply, the voltage will drop because it can't supply a sudden amount of large current and maintain the voltage. And that's the same problem they had on the DB04r first gen, so there's nothing new on there. It's actually better handled, I think, than the first one. Here is the actual pulse length of a firing. This is from the MOSFET gate. So we can see that's about 1.6 seconds, is that? Well, I think the first one was 2 seconds, but it's slightly shortened the pulse that it fires for, the length of time it fires for. But again, that still will quite easily fire a Talon or an igniter, any match. Here we have the current draw, and this is of the first generation. So I've used a current sense amplifier which is attached in line with the device on the test. So what happens is I have the amplifier that sits before the module, and then the module gets fed from the amplifier, so I can see how much power is being drawn, how much current is being drawn from the unit under test. This is standby. This is with no igniters connected. So you can see we've got about 2, 4, 6, 8, 10, 12, 14. That would be 16. So that's nearly 15 milliamps. This is generation 1. If we go to generation 2, you can see it's dropped a bit. So we now have 2, 4, 6, 8, 10, 12, 14. So you've got about 13 milliamp constant standby draw. And again, this was with no igniters. So you can see there's not a huge difference between the two realistically in terms of standby. It's only a milliamp in it or so, 2 milliamps in it. This is a trace of the gate of the MOSFET when we turn power on. The previous time we looked at this, we had huge amounts of contact bounce from the switch affecting the MOSFET. You can see here we have a small pulse of about 400 millivolts, possibly less than that, because as I say, this is not necessarily probed well, so this could be looking worse than it is. And this is just because the system's starting up and it's slightly unsteady, so it's very difficult to take a measurement at that stage anyway. but there's no massive noise marks like there were in the previous model. So bounce is not really affecting the MOSFET, which is good because you don't want switch bounce to affect the far end MOSFET because it could fire when you turn it on. It's the danger. Here is the switch trace for the bounce on the 6-volt rail. So you can see when you do switch it on, there is a degree of bounce there, but that is very short compared to the previous version. So if you look at my previous video, you'll find that the bounce of the rocker switch is a lot worse than that. And here is the power down of the module, because obviously you've got capacitors there that you want to drain off. You don't want to leave them charged. That will make a very dangerous state for the system. So it does slowly drain away. So that takes about, what's that, 1, 2, 3, 4, 5 seconds to drain away. That's not too bad. Let's now quickly look at the I2C line, which is the communication between the PIC chip, oh sorry, not necessarily the PIC chip, but the microcontroller and the memory. And this is problematic for me because every time it communicates, we get a lot of garbage. And this is obviously the microcontroller is stuck in a loop here. I've got no idea what's happened is the answer, but this is a firmware issue because over here we have the packets which you should see, and then either side of that you get this noise every single time on the I2C line. It's almost like it's locked up for some reason. It's waiting for someone else to acknowledge, or the microcontroller is just sending the same command constantly for some reason in that time period. But that's the only fault I could find. Let's look at rather than look at all the I2C communications, I'll just give you a brief overview of the memory addressing. So we're memory addressing from 00 to 0F. On power on, we read everything from 00 to 0F. Now, when we fire a Q, we get no communications. On the previous model, when you fired a Q, it read the Q information again. That doesn't happen anymore. So we seem to load all that information into the microcontroller to start with on power on, and then that's it. We don't get anything else when you fire a Q. If we program Q1 to the remote, button 2, this is where it starts to get interesting, because we write from 00 to 02, and then if you look at the second digit of 02, that changes to the button number, sorry. So we've gone from 11 to 12. So we've gone from button 1 to button 2. Now the 1E231, you may ask, what's that? That is the unique identifier of the remote we're using. So every Q holds the identification of the remote plus the Q number, the button number, sorry, it responds to. So terminal 1 responds to this remote, button 2. And then 03 to 05 would be terminal 2. Then 06 to 08 would be terminal 3, and then 09 to 0B would be terminal 4. 0C to 0F always seems to be the same data. I'm not too sure what that is doing. If I'm honest with you, that could be because it's from another module which are using the same firmware for, which has 5 terminals. I don't know. So again, I've done another program Q2 to remote button 3, and if you look, you've got the same idea of the remote, but the 3 changes. So it's gone from a 2 to a 3, so from button 2 to button 3. Now, I tried this out. I went and I programmed Q3 to another remote, Q4, on button 4. And you can see that it's now changed from 1E231, which is the address of one remote, to CC09A. So that's the other remote I've got, a different remote. And again, you've got 4 as the last number. So that's saying that that's replying to button 4 on the remote. So you can not only program each queue individually to the remote numbers to whatever number you want, or whatever button you want, you can even program different remotes onto the same module. If I press the front program button, so these ones we're using the white buttons on the back with the individual queue programming buttons. If I use the button on the front, which is the sequential program, it writes the whole all across all terminals sequentially, as sounds obvious, isn't it? So on this one, I pressed button 1 to start with, and if you look, this is on a different remote from the first one I was using, and it's recorded it as terminal 1, button 1, terminal 2, button 2, terminal 3, button 3, terminal 4, button 4, so 1 to 4 on this different remote. And again, that was just by pressing button 1. So now I tried this again. I did sequential program, but I pressed button 4 on my remote again. And this is the other remote now, if you look, this is the 1E231. And again, it's gone from 4, 5, 6, 7. So it's gone sequentially after just pressing the one button. This is exactly the same way the previous generation 1 worked when you had that front button program on the front of the module before it had the individual programs. And at the bottom there, if you look, I've tried to program 12 to 15 on it, which I don't have buttons for. I've only got up to 12. So I have then used the binary numbers, and it has actually programmed that. If you look, it's gone from C, D, E, F, because this is obviously working in hex, which will give you the 12 to 15 buttons. And if you use my previous video about using the binary weighting, so you do where you got 1, 2, 4, and 8. So obviously if you did 8 and 4, you'd get 12, 8 and 4 and 1 would get you 13, etc. And then I've looked at doing the special function buttons when it's not programmed on the queue numbers, so I've reset it back to 1, 2, 4, and then I tried doing 13, 14 and 15, which used to get special functions on the previous generation 1 model, such as all fire and sequential fire. They don't exist in this unit, so that obviously has been taken out of the firmware. But you can program the firmware to include those numbers if you so wish. So, other than the I2C line being a bit of a mess, it does seem to be working quite well. Now I want to figure out the actual voltage it's set to become low battery. So I've got just the power supply here and the unit we're testing. So I'm going to turn the power supply on, it's set to 6 volts. So unit's on OK. Let's now take the power supply down at 100 millivolts at a time. Try and see if I can do it as you can see. My guess it will be somewhere close to 5 volts. Okay, we're lower than 5 volts now. Oh, we've got the low battery indicator on now at 4.5. That's interesting. Let's go up in 10 millivolts and see when it turns off and see if we can actually find the trigger point a bit more precisely. So we're at 4.63 volts. So if we drop down, so 4.6. So around 4.6 seems to be the magical number. Let's drop down below that and trigger low battery. Because what I'll be interested to figure out now is whether that stops you from firing the module. Because that would be really bad if you're in the middle of the field and it went low battery and you couldn't fire the module. So you can just about see we've got low battery, we've got the queue in. Let's fire the queue. Now that works okay. So that's fine. However, obviously the problem we've got is that we're at 4.6 volts, which is below the 5 volt regulator. So we're now actually effectively running the linear regulator below its specified voltage. Although technically the logic chips will be able to handle that, it's still not a good idea to do that. So a couple of last thoughts for the module. I find it's really interesting that they've gone to the extent of programming the individual remote codes into the queues as well, but they don't seem to advertise that as a feature, so you would never necessarily know unless you tried it out and happened to be lucky that the different modules queues can actually take different remotes. That could be a useful feature. You could also, looking at the circuitry because of the regulator and that, potentially run this at a 12 volt battery rather than a 6 volt battery. However, you need to look at the heat and temperature coefficients of the regulator and of them firing MOSFETs, because obviously the current will be high going through the MOSFETs, and whether or not they have enough heat sinking to cope with the higher voltage or not. If it could be done, then potentially the unit would have a lot better reaction to longer cables than that. Obviously the higher voltage, the better you'll get in terms of the results you'll get in terms of long cable runs. The other things to look at are that the I2C garbage is a little bit disappointing, because obviously that's a firmware error. They should have tested that out and worked out why that's causing it. The first version didn't have that issue. I like the idea of the difference between green continuity and red fire. I like the idea that the batteries, the LEDs, are off when the unit is on until you've actually put igniters in to get the continuity lights rather than always have the LEDs on. I think that's a much more logical way of looking at it from the end user's point of view. I prefer the fact that this is regulated rather than just running from the 6-volt power supply. The change of switch from the rocker switch to the slide switch is great because we have lost the bounce noise which was on the far end MOSFET, which technically could have been dangerous, but to be fair, I haven't managed to prove that in the first gen, so that's just still a theory. We have also lost the special command codes 13, 14 and 15 in the most recent generation. Maybe that's a feature they have removed from their other models. Maybe that's more of a professional model sequence now, where you had sequence fire and all fire, etc. So that sums up my analysis of the module. I hope this video has been helpful.